Hi, I'm Max Hawkins. I'm a third year computer engineering major in the Randall Research Scholars Program, and my research is in coordination with Breakthrough Listen and the Berkeley Center Research Center. Today I'm going to be talking about high performance radio telescope array data processing development. I get that that's a lot, so you can think of it as improving the performance and usability of data processing. So, a brief background on radio astronomy. It's similar to optical astronomy, which you may be familiar with, like looking through a eyepiece of a telescope to look at the moon, but it operates in different frequencies. So it operates on wavelengths that things like your toaster oven or your Wi-Fi signal is, rather than the optical frequencies that our eyes naturally detect. An important aspect I wanted to highlight is that in radio astronomy, you can see during any time of the day. You don't have to wait until night because the frequencies that radio astronomy deals with, those don't diffuse through the atmosphere in the same way optical light does. It's also lower resolution. Instead of getting like a nice, clean, pretty picture all at once, you usually get a single pixel. But in this pixel, there's a lot more information than an RGB pixel. They're also extremely sensitive. As you can see on the right, that is Arecibo. Rest in peace. It just collapsed earlier this week. But this is it in its prime. And you can see that it has a large collecting area um, because it needs to collect a great number of photons from these distant galactic objects to be able to determine the scientific properties of them. But radio astronomy is actually trending away from these giant monolithic telescopes towards multiple smaller telescopes forming radio telescope arrays. These offer a simpler mechanical design because you're not dealing with 100-meter dishes, you're dealing with typically 10 to 40-meter dishes that are easier to mechanically design. But you pay for that with signal processing because you get a data stream from each of the antennas rather than just one. And so you're dealing with much more data. But you also have much more complex data processing because to get the same sensitivity that that single large dish would offer you, you have to intermix the signals from all of these antennas together. And that is obviously much more complex than getting the raw data stream yourself. Specifically at Meerkat, which is a radio antenna array in South Africa, and this is specifically what my research is initially applying our scheme to. It is 64 antennas and it generates 27 gigabytes per second, which is absolutely insane. You can see what it would be like over the course of a day, even operating at 50%. But it's going to get even worse. With the square kilometer array, mid and low combined will generate 159 terabytes per second. It will generate more data than comes online onto the internet, which is insane. So to handle that amount of data, you have to have very specific and very high quality data pipelines. Let's look specifically at Meerkat. Um, Coming from the antennas on the left, we get 64 digitized antenna data streams. And there's a whole lot of other complex things to deal with, but we can basically boil it down to, we get the data over this 40 gigabit Ethernet fabric, meaning we get it as network packets, like Wi-Fi packets, basically. And those have to be pre-processed with this input thread that packages the data into something an astronomer likes to deal with, and that's put on NVMe buffers. Basically, those are high-speed memory storage. Now, when that's in the buffer, it tells the GPU or it tells the CPU or the calc thread, okay, your data is ready to go. Start doing your thing. And depending on what the astronomer decided to do that day, it would operate, push data to the GPU, send it back. And the end goal is to not save all 27 gigabytes per second, but rather save a small amount of that data to hard disk storage that can later be fully analyzed by an astronomer. And in the case of Breakthrough Listen or the Berkeley City Research Center, we are trying to search for signals of extraterrestrial life. But other astronomers are doing different things. So we want to make this data processing work for them as well. So to get these massive data transmission speeds and calculation speeds where they need to be, we have a bunch of low-level details that happen. So we buffer the input and output. There's multiple pre-processing steps, like I mentioned. You have to manage shared data to make sure that multiple processes working on the same data don't corrupt it. There has to be a straight handoff, and we do that with low-level semaphores. And you also have to transfer data between the CPU and GPU. But we want to abstract all of that away from the user so that they can focus on calculating their intermediate data products that are used in their search algorithms or whatever algorithms they end up using. And so that they can focus on defining the thresholding. So they can define what is significant, what do we save, what don't we save. And that all leads us to the end goal of running a custom algorithm on a high performance pipeline without having to program in C or CUDA. Specifically, rather than C or CUDA, we program in Julia, which is very similar to Python in that it's a high-level programming language. But in my opinion, coming from Python, Julia is much better, and it offers the speed of C essentially with the ease of programming of Python, or that's what they claim to do, and I think do decently well. So my work is over to the left in the green box, and I'm basing my work off of these data formatting libraries and this hash pipe library, which is written in C. And what this hash pipe library is all that low-level stuff in C. But I don't want the end user to have to deal with that. So I wrote these wrapper functions in Julia, which is found in hashpipe.jl, that exposes all of that low-level detail at a higher level in Julia. I also wrote search.jl, which provides a framework for all future search or calculation algorithms. So helping define what is common across all of these to help better create some generality in the system. As an example of one of these algorithms, I implemented spectral kurtosis, which is a statistics-based algorithm that determines signal interestingness based off of its Gaussinity or its power distribution Gaussinity. But I combined all this together to create this hash pipe search demo thread, which takes all of this C code, wraps it into Julia, and is running it on a demo, is running an example algorithm on hardware that is very much like the hardware found at Meerkat or found at other radio telescope facilities. And it's meant to show you don't have to be an expert C or CUDA programmer to be able to do these things, because we can't force engineers to be perfect astronomers, and we can't form or expect astronomers to be perfect engineers. So I'm trying to bridge that gap. So in the future, I want to deploy my code as Julia packages so that anyone around the world can just import my libraries and use them natively. We're also going to work on potential publication materials from this. But really what I'm most excited about is NVIDIA Tensor Core utilization, which are these, it's high-speed dedicated hardware on GPUs that's meant to improve machine learning performance, but it also can greatly increase digital signal processing. As you can see on right, this is correlator performance graphed. And correlation is an algorithm that's frequently used at radio telescope arrays. And you can see that just using a regular GPU core, and if you're not using tensor cores, you're losing out on basically an order of magnitude of performance that you could get. Also want to make offline file processing so that you don't have to be running this at an array. And then I want to work with Gay Lunita at the New Jersey Institute of Technology, developing and validating spectral kurtosis as an energy detection algorithm on radio astronomy data. And so with that, I thank the following people and open it up for questions.
Max, what are some of the other algorithms that you see being able to run on this one?
Yeah, I actually have a little graph handy here, not graph, a little graphic. And I anticipate, like I said, correlation is heavily used. So correlation is how you synthesize multiple of these antenna streams together to do different things. Also, you need to sometimes need to sum the antenna data streams together, or we could run machine learning energy detection on this data, anomaly detection. We need to run candidate triage, determine what to save, what to throw away. Beam forming is you can basically digitally steer where the telescope is pointing. And then there's a lot of like really domain specific algorithms.
So, as a Python user, is Julia worth the switch?
I consider myself a little bit of a Julia shill sometimes because I think Julia is pretty awesome. I I love Python too, but Julia, it really is faster. You can see that on this graph that it's in order to 2 orders of magnitude faster at certain benchmark tests. Um, and I think it has better CUDA integration or GPU integration, NVIDIA GPU integration. Um, and so I think it's easier to build things at speed in Julia rather than Python. Machine learning wise, I would probably stick with Python though.
You mentioned that this was like a framework. What sort of facilities do you see this being used at?
Yeah. So this framework we're basing it off of HashPipe, which is that C library that does all that low-level stuff that I talked about. So any place that uses HashPipe, hopefully we're planning to use this framework as well. So that's places like the Green Bank Telescope in West Virginia, um, Meerkat Telescope Array. The primary one that we're focusing on that a lot of astronomers have been working towards for the past decades to build up and actually start as a major radio telescope array is a square kilometer array. So I guess if I had to pick one, that'd be the most significant one that I'd say. But there's a list of probably a dozen or so telescope facilities.
Very good, Max. Thank you for your presentation.